Well, hello, and welcome to Old School Coding, where I'm using some programming language from the 1990s, using some techniques from the 1990s to construct a simulator of a microcomputer from the 1990s. So, let me get the camera fixed here real quick. There we go. I don't have to slouch down quite so much to be in frame. So what you see on frame is basically a summary of what we've constructed so far. I've been thinking. We have a lot of duplicated code. I have been fairly open about grabbing implementation from one chunk of stuff and copying it into a new thing which is slightly different and then editing it. So it's called clone to own. And the usual endpoint of clone to own is that you take all of the versions of something that have been cloned and modified, and you look at them and you say, can I combine them back together again? Okay. Now, if we were not trying to squeeze every frippin' nanosecond out of this thing, a lot of this would be driven by Booleans. We would come in and we would keep track of what machine cycle we're in and whether we're doing this or that. And then the logic would say, if we are doing an I/O operation, this is where we do this, and so on. So it would be a whole bunch of conditionals and trips to memory to get data, but it would mean that we would only have a few methods. And in fact, an 8080 simulation can get fairly compact if you do that. It can get even more compact if you're not working in a framework where everything you do in this function has to happen as a result of one edge, and you're supposed to return and then let the surrounding framework advance time and call you back. So there are some things we can do that would make this run a lot faster. In fact, in the limit, what you do is you look at the instruction sequence, you say, what is the fastest way I can deduce the final state of the processor and the system after it has executed these instructions. But our goal was to be able to reproduce the timing diagrams. So we want all the signals to wiggle at the right time. Anyway, so I have taken all of the bits of code that we've written for implementing t-state number 3 for this operation and so on. I kind of lined them up here and started coalescing them. And what I found was that there is a lot of commonality, of course, and there are some differences. And the question is, are the differences enough to continue to justify keeping all these things separate? And I think for now, the answer is yes. In the long run, we may want to start coalescing things. So we have essentially 6 types of machine cycle. There's one that I don't list here. We've got memory operations, memory read and memory write. We've got I/O operations, I/O read and I/O write. And these are all just slightly different. For instance, memory read and I/O read differ in a few things. If we start abstracting out some of the things we can set up, so I'm assuming that we're going to use macros that have parameters substituted in. All of the cycles that do memory reads, there's some place that they're getting the address from, and that gets latched into IDAL. And that might be the PC, the stack pointer, HL, DE, BC, and so on. Status might be status M read, it might be status fetch, it might be status S read. So there's actually separate for instruction fetch, memory read, and stack read. Let's put the memory stuff together. So here's memory write. Memory read and write are fairly similar at the start. They both have the possibility of incrementing or decrementing the register pair. So we take the IDAL and we latch either the incremented or decremented value back into the register pair. Now, not all these are valid. For instance, the stock timing diagram does not include the possibility of decrementing the register pair, but as you'll see when we get to our final instruction down at the bottom, which has some errata, we do need to move the stack pointer both directions. And that's going to require that. Memory write, I think all of our memory writes that move the register, I think the only place we do that is push. So the only way we'd have that would be dec. But if I include a potential for increment here, this makes these two cycles much more the same. Read and write differ in whether debian is there or not. And I've got a note here, no TW. I still need to find out authoritatively whether the 8080 supported wait states during write operations. Simulation as it stands can't, because the target device is not getting any kind of control until we hit WR down here in T3, which is entirely too late. In the hardware system, we do have a chance to observe our address and to know it's a memory read or memory write well before that. It's only the way I wrote the decoder that makes the wait state during memory write awkward. And the reason why I want to research that is if that's true, and if I need to simulate wait states during write, then I need to rewrite parts of my decoder. Not a hard thing. It also will mean a runtime penalty, because now, here in T2, where we are releasing sync, or here in T1, somewhere in here, after we've set the address, and before, so sometime in this bar, so between the address be going out, status going out, and here at phi2 falling in T2, we decide whether we're going to do a wait state or not. Somewhere in here, the memory or the I/O device has to get control somehow. And the way we've been doing that is when dbin triggers high, we've been delivering control. And we would need to do something else. So dbin says we're ready to move the data. WR says we're ready for you to receive the data. But we would need to have something else happening up here that says, oh, the address is valid. Go let the remote device know that we're addressing them. We don't, we know whether it's a read or write. That's in status. Status will tell us read or write, I/O or memory. But we're not ready to move data yet, but here's the address. At that point, the remote device can come back and say, I am ready or I am not ready. So that would be an additional chunk of work. I'm not sure when I would do that. I would have to look at timing diagrams and find out when it is most likely that remote devices would be informed that they have valid data. And I think that's going to be based on the output of the status latch. Anyway, so this is where we are with trying to unify all of these bits and pieces of T-state management functions, trying to bring them together. Like I said, we still have a lot of things to think about. You've heard me mention a bunch of them. The T-state waits, if I put the reads and writes together, we notice the I/O versus memory, very similar. Now, I/O ports are always using the ZW register pair, okay? And they're always sending the data to the accumulator or from the accumulator. But if I mark those as DDD or, whoops, I/O bright is, okay, I have not yet finished filling this guy in. But at some point, data equals, our data has to happen. To do include where MW and IOW set data. I literally just started pulling this table together this morning because I thought, hey, this would be cool to do. And it didn't fall together as good as I'd hoped. Anyway, so at some point, memory write and IO port write are going to send out the data, probably T2, Phi 2 rising. I don't know. This seems like a good time. I mean, we, in the reads, I discarded the things where I say I am tri-stating because that's kind of not that interesting. But I could do this, data : equals dash dash dash. To do verify MW and IOW assert data, publish data at Phi 2 rising. We do not set DB in. That's the wrong direction. We do WR down here in T3. This is the interesting thing about the write cycle is that it happens during T3 completely. The actual hardware doesn't release the write signal until the start of phi 1, until here, this edge right here, phi 1 rising. Come on. So this edge right here that I actually got rid of the line because nobody does anything on this line. This is where we would normally release WR, but that would happen in every cycle. It would happen every time, because if we have a write, who knows what's next? So every machine cycle would have to be diving over to check that WR is not set. So that's why I tightened up that timing. Anyway, that's either here nor there, because we're not going to attack that this go around. What we are going to do is start to work on push and pop. And that is here. Not yet implemented. There we go. So call. So we've got call, which has a 16-bit immediate destination address, and it pushes the PC of the next instruction onto the stack. The conditional calls will do the memory cycles that fetch the next the immediate, and then they will decide whether to jump or not based on the condition. They evaluate the condition early on. Let's take a look at the PDF. Time to go to the PDF here. See, call here. So M1, T4 to T5, we are latching the SP into the IDAL and then decrementing, taking the decremented IDAL back to the SP. And then we have an M2 cycle where we are fetching the next byte. So this is a 2 bops, and we get that into Z. And then we have a 3 bops that gets it into W. And coming out of that, we say, okay, well, we've decremented SP. So SP now has the address of the first byte to put out into memory. And it's the high byte of the address, because we're going to be decrementing. High byte goes at a higher address on the 8080. So PC high goes to the data bus. So during T1, we send out SP. During T2, we write the incremented SP back into the stack pointer, incremented IDAL. And that gets PCH, that's a memory write cycle into stack. Then we do it again, memory write cycle into stack of, again, PC low. PC isn't changing during this time, and it will represent the address of the next instruction. So these guys did WZ. So during the next T1 cycle, it's the WZ value is the value we want to read. And the way I've handled that previously is that at the last moment, in the last cycle of the conditional call or the conditional jump or the jump, I latch the value of WZ into PC so I can use a normal M1 cycle over here. I don't want to be messing with the M1 cycle and having every M1 say, wait a minute, am I using WZ or am I using PC? Because this is a rare case. The other alternative, of course, would be to duplicate the instruction fetch and say, oh, well, we want to duplicate it so that we can say, well, at the end of this, we're going to use this alternate. But then what do you do about interrupts? Okay, what if you interrupt here? You'd have to know when I come back, you'd have to know, first of all, the interrupt has to stack the WZ value. Oh, no. So, yeah, we're going to latch it into the PC at the last moment. So call is a lot like jump, except we're adding stack ops at the end. Let's get rid of the PDF and get into source. So looking at jump, I am going to duplicate jump and make it into call. And again, this time we're starting with the implementation rather than the test. The test for call, I don't have return yet, so the test for call is going to be the same as the test for jump, plus a verification that the appropriate values were written to the memory. Okay, so there's that, and underscore J becomes underscore C. So name C, condition there, C naught, C naught. I believe these are all correct. I will check those in a moment, although actually the compiler will check those for me. Okay. Before we continue with changing the J's to C's, let us check the numbers that just got locked in. No, that's correct. We didn't lock in a number. FB is literally the flag bit. Okay. Continuing with this, I need to also make sure that I don't change underscore CY to underscore C by any chance if I've got an underscore carry anywhere. So always check J naught, J naught. So if I let this run, it would basically call instructions would do the same thing as jump. They would not actually they wouldn't actually push the return address yet. And I think that's actually worth testing, because that's most of the functionality. Adding on the stack push is like gravy. So we need to go into inc i8080 impl, wherever we have a search for JMP, duplicate the line, and change JMP to call. There we go. It was only the one place. Opcodes, we have the opcode, no phase changes, no status changes, test. So there is no jump post. Remember, jump and call are handled entirely internally. Remember what we did when we collapsed everything together? Because there's no jump test here. I8080 test. When we do jump, it just has jump test.hex. So I'm going to need to put call in here. So where we have LDST, I'm going to change it to call. So call will in fact use call test.hex, but it will also be testing the contents of memory. And that's it for those guys. So now it does the compile and it says, oh, I don't have call post or call bist. Okay, so let's set this up. So who also does a whole bunch of, runs the hex code and then compares stuff in memory? Well, goodness, MovM, I believe, does that. And we're going to do the same thing. We're going to need to be comparing memory. So I8080 MovM test, change MovM to call, test the call and conditional call. So set the RAM to a known matching pattern, run the program in call test, and then check that the right data is written to RAM. So if I less than, bu- bu- bum, bu- bu- bum. So the other thing that I did somewhere was I pulled out prep, and let's take a look at the tests really quick. There's one of them that actually did a better job at doing it before and after. Which one was that? Yeah, LDST. Tested it in test phase. So we're going to use LDST as our base. Oh, come on. Top. LDST. Come on. I'm not sure what I did. Sometimes I get caps lock set, and under Emacs that does change what commands are executed. Control X, Control X F is different from Control X capital F. But this is call test. So we do a call test init and call test fini, and this is going to do check that appropriate. RAM cells have been written with return addresses. And that will all depend on how we set up the stack pointer. It depends on really what the test looks like. So first of all, we want our test to basically test that call acts like jump initially. So we copy jump test into call test.asm. We change these conditionals. Okay. Control J, Control I, J becomes Control J, Control I, C. JC becomes Z. Now these labels I want to change to I suppose I could have changed those at the same time. And CM call, something tells me this is not really a valid thing. Oh, so in my macroized stuff, I had opcode P for pass. So we have a JMP, which is a label. This may not be playing nice with some assemblers. I'll make it okay at the end. And I'll put an underbar in just to make it sure that it disambiguates. OK, colon becomes underbar. OK, colon. F1 colon becomes underbar F1 and colon. F2 colon becomes underbar F2 colon. So opcode underscore result. Fail, fail 2, fail 1, et cetera, et cetera. And that avoids having a label with the same name as my instruction. I'll go back to call test. Jump becomes call. Unfortunately, that means that these underscore OKs and underscore F1 and F2s are going to be long in some cases. Let's think about this for a moment once we get it all done. And I'm going to change the instructions and the branches. And I just realized I didn't change these labels here. There, JMP call. J becomes C. So I think the only places where it becomes too long is just this one place. I will use P here. And this should now be correct. I believe failure to assemble is not showing up as a problem here. I need to actually look at it. So jump test. Okay, that's assembling properly. Call test is not assembling properly, however. Lordy. There's call test.lst. So call test.lst is assembling properly now. There we go. I needed to start my build loops going. And now we are getting an error. First of all, we are not using the symbol, the ROM symbol. Well, actually, for the call test, we don't care about the contents of ROM. We are going to be looking at return values. And this says that I am not actually hooking up the instruction. Well, not a surprise. So let's hook up the instruction. Source i8080.c. And over here we're getting into source i8080call.c. So call init's got all of the stuff set up. So now we just need to get in here and find, was it LDST? Or let's go do JMP. Yeah. We're putting it after LDST though. There we go. And that ran. It didn't error out. I don't know whether it worked or not because we haven't verified that. Test 8080 call test. Let's put in a print top, and print end. And we are getting there. So we are executing these, and it is not reporting an error. And it should have dumped in doc image like that. Let's dump the calls out here, regenerate them, because this may have generated from the first time it attempted it, which may not be working. So now bist call. So LST call test, LST. So the first subtest is just the call instruction, which looks just like a jump at this point. So IR is CD, so we get our 0E, move C1. Okay, and that does set C to 1. And then we do our call, and we get our Z and W coming in, so 0006. And indeed, we do end up branching to 0006. So we should not have even fetched from 5. And if you look at the address bus, you see 0, 1, 2, 3, 4, 6, 7, so on. So we did not even fetch from 5. That's correct. We called past it. So that's working. And then we work through the conditional calls. Again, this is going to be call non-zero, call 0. So the address bus is 89A, B, C, D, E, F, 10. 1, 2, and 1, 3 should be getting skipped. 0, 1, 0, 1, 1, 2, and 3 are skipped, and we resume with 1, 4, which is the end the plot, please. Well, not followed by next subtest. So these guys look good. We should see the same pattern for all of them. Looking just real quick. So these are executing as jumps with the call opcodes, and the conditions are being properly handled. Okay. So what we're missing here is the stack ops. M4, T1, T2, T3, push PC high. Okay. Let's bring back our PDF really quick. And I just want to, oops. I just want to look at the left-hand page here. And actually, let's shift ourselves to viewing just the one page. There we go. So call. We have the parts here. Judge condition, manipulating the stack pointer is not done yet. We're not doing the stack pointer yet. We need to put that in. So while I'm editing this, the PDF is actually behind the editor. The other trick is that during the call, judge condition if true, stack pointer -1. And this just says stack pointer -1. So we want to make sure we're doing the right thing during the judge condition. So this is M1T4, and we do have an M1T5, which is here. M1T5 is going to be common. It basically does nothing. We're going to do everything in M1T4 except, we need to rewrite the condition down here in M1T5. So M1T4 basically is saying, here we go here. And we also need, if we are going to be doing the call, I need to copy the stack pointer into the IDAL. So we can have a J M1T5 and a J not M1T5. And I think if we do that, no, because we do need to patch the correct opcode here. So this is based on what condition code we've got, and these guys are not. So if we are doing the jump, SP to dec of IDAL. And J naught drops down into C naught. Stick J is state C. So it's not jump, it's call. So kind of important there. Again, these are static, so they only have file scope for source code. But in the debugger, I need these names to be unique. I don't want to have the same function appear statically in two different source files. Or in the debugger, it's going to be hard to differentiate between them. It's like, is that the foo in this file or the foo in that file? So the difference between the C and the C naught are just on whether we are decrementing stack pointer or not. Now, one hopes that between phi2 rising and phi2 falling, this doesn't change. But if it does, then I need to actually commit this here. I am wondering, let me check my CPU implementation first, source i8080.c. Make sure that we're only honoring state next in the right time. So during phi1 rising, we are sampling state next. So it's okay to set it early. Make sure this is still running. Okay. Dset, passing argument from incompatible pointer type. Well, that's because we need to use a set to set the stack pointer. And we need to use a set to set the IDAL. Add in the missing forward declaration. So I state call M1T4 is declared static but never defined. Well, we need to do real work. Now, the jump just used a 2 bops, as we can see there. Oh, and it's M1T4 that it was mentioning here. Yeah, okay, that's my T4 and T5 stuff that I need to implement. But that did trigger a thought that we do now have to have the call instruction go to the right place. So call is just like this macro, except it is going to be always true. And let's do that first. I8080 state call M1T4. So it always jumps, so the else clause goes away, the if goes away. We do not change those because M2T3 of the call instruction would always be set, right? Let's make sure. M2T3 of call and M3T3 of call. I'm going to bring those up to the top. These guys are set to not. They will be changed back and forth between C and C not. Let's put the knots up at the top here because it's the calls that get long. 2T3, 3T3, 4T1, T2, T3, 5T1, 2, 3. There we go. There we go. And I am going to change this guy to use the word call instead of C not. How are we doing now? So M4 and M5 are not yet done. Okay, defined but not used. Carried forward our comments on what we were doing. And in the to keep this kind of like what I was doing here with moving the knots up to the top, I don't, no. Let's move the knots down to the bottom. And we can move the knots down now. I really should have memorized by now exactly how many of these guys I need. So I do like the idea of centering that line so that centered text below it is centered neatly. So for branches not taken, I believe that a call not taken and a jump not taken are exactly the same. So we're going to do the same thing. M1T5 will hop into bops, 2 bops T1, which will gather the data into Z, hop into 2 bops T1, 3 bops T1, gather the data into W, but this is a red M1 int. Since this condition was false, do not copy WZ into PC. Bom. Okay, so now we need to knit together the whole push stuff onto the stack thing. So, M1T4, call is going to say, put SP into the IDAL. This should be common between the call instruction and the if true. So this guy is the call instruction and this guy is the call conditional. And we're getting the right thing here. Implement the conditional calls here. Call M1T5 is common. We're going to do the call, so we need to decrement SP to get the proper address to start pushing. M2T3, we're receiving 1 byte of the call address. This would be the low byte of the destination. Then we receive the high byte of the destination. This is not a red M1 int here. Notice that there will be a difference here for not M3T3, which will have this final. And I did some of that coding behind the PDF, didn't I? Boit! Narf. Okay, so call M3T3. Call here. It's going to be these 2 lines here for call and call conditional. You notice they're exactly the same. Footnote 13 says, if the condition was not met, subcycles M4 and M5 are skipped. Processor instead proceeds immediately to M1 of the next cycle. Okay, so that's our call conditional, terminating there. So we are continuing with the call or the conditional call taken. M4T1 is a memory write cycle. What would be our best memory write cycle to look at here? How about load store? So the STA M4 cycle is our best memory write that we can look at right now. We will need to change some things. So during phi 2, oh, we don't have any of the guts of it. So IDAL here is getting val of SP. And this is a stack write. Let's put that at the top of the window there. And then the T2 cycle we drop sync and we set the address, and this is the val of PC. So we do the high byte from PC goes out on the data bus. And this guy needs to hook up to the appropriate. All right. We do not want to be diverting over to STA. Thank you. There's PCH. And then we look at the T3 cycle here. And we are not doing this because we'd have more work to do. What are we missing here? Well, we need to change the stack pointer. Stack pointer needs to be decremented. Well, we can pick up the place where we decremented the stack pointer before. In the process, I am checking that we actually did it. Yes, there is a set of SP IDAL. So during M4T2, we drop the stack pointer back into where it's supposed to go. Now M5 is just like M4. But of course, here we say raise ret M1 int. And here we are moving the low byte of PC into data, and that works just fine. So if we're going to do this, then call test needs to establish a stack pointer. And I'm going to start it at 128, and it's going to work down. So I could do 64 pushes before I ran off the top of memory. And I am going to be doing 8, 16, 18 pushes, so we're fine. Now, the actual values that it's going to push have to come from calltest.lst. Oh, boy. Oh, boy. You know what I can do is I can go in here, and I am going to So starting 80 hex and going forward, I'm going to put in DWs for the labels in the order that the calls are made. Ba-ba-bum. So all these calls, I want to take the following label and put it in a DW. How do I do this? Search for semicolon, semicolon, tab, tab, C. Go to the next line, search for a colon. There's our label. DW label. Now, I don't believe that actually caught everything. Yeah, see, I've got a call non-zero here. So I need more labels. Call P, colon Z, F1. So where we have these colon Z, F1s, and so on, I need an F3 coming in here. So underscore F1 new line. We're going to come in here and we're going to go there. So that gets F3 labels. Let's do the call manually. Okay. So the rest of these, F1, we're going to have the label F3 and then the label F2. Oh, there's an easy way to do this. Search for underscore F, 2 or 3, followed by a colon. So starting at 80 hex, we have our return addresses laid out in reverse order from how they're going to end up on the stack. But each word is in the same order. See, DW is going to put out high-low. So we can't just compare the bytes in reverse order. We need to compare the reversed words. I think... Yeah, I think we can do that. I'll call that pushes. So why is this not Oh, because my testing was looping forever inside something. It is likely at this point that one of my instructions is doing just plain the wrong thing. Okay, so desk check. I like to put the stubs in as I'm desk checking. That way, if I don't find anything in my read through of the code, then the next run it will show me what's going on. So, first of all, I'm going to say here that I am latching a value into IDAL, branch not taken, there. When we do the M1T5, we get the value decremented into SP. There's our value into Z, our value into W. Here's where we force the branch address into PC. We're doing that before the push. We're doing that before the push. Oh, lordy, 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 lordy. We want to do that after the push. So instead of M3T3, that happens in M5T3. That could have been the mistake right there. But let's continue getting the stubs here. M3T3, we're grabbing W. And then once we've got WZ, we do not want to tri-state them. Thank you. We need W and Z to continue until after we copy them into the PC. So here we there's the address. It is a stack write. There's the data. We hold that all the way through the write and then tri-state the address. That's fine. PC, value of PC, and there we go. Okay, so we're still running forever. And nothing is really, well, we don't know whether it's printing or not. Aha. Okay, so IDAL gets that. SP gets decremented. We read into Z. We read into W. We read into W. We read into W. We read into W because M3T3 is not setting the next state. Okay, so that looks better. So IDAL starts, test starts. Get a value into IDAL, SP decrements. M2T3, M3T3. Oh, 0909 1717. That's not right. Something is wrong with that. Oh. Helps if I consistently use macros like this so that I don't come up with problems like this. SHOVW. sure that's still working. SHOVW. Did it just, we just reverted to something? Hold on. Oh, we still have live coding.standard error with this crap in it. Well, let's see. Let's go back to running bin loop over there and running report over here. Okay. So IDAL is 8 decrements to SP. Adder 6 gets 9, adder 7 gets 0. So there, branch not taken, yada, yada. So it comes all the way through, and we get down to I-8080 call test, where we're failing, of course, because we're not doing the right thing here. We do need ROM. Going to add one more thing here. What I want to do is have this describe what's going on. So what we get here is a byte saying how many pushes we should have done. Okay. Followed by the words that were pushed there. I'm going to mark these const so that I don't modify things like const byte star exp is equal to ROM plus 128. Const byte star obs equals ROM plus or RAM plus 128. Int check is equal to star exp plus plus. And I am expecting 8 conditionals by 2 for each direction is 16 plus 2, so I'm expecting this to be 18. I think I can remove those SHOs. Well, they're not causing too much of a problem here. This says that the expected value, hold on. No, that is CHK. And the expected value is from ROM. So we should be getting 22 hex here. And we're getting 5A from the ROM. Well, it helps if I actually read the ROM. So the value I'm getting here from CHK is double it. Ah, 17 because, right, it's 8 conditions times 2 is 16 plus 1 is 17. So actually, let's CHK slash equals to convert to words, bytes to words. This is 34. So what I want to do to check is I want to say observed minus equals 2. So observed now points to the 2 bytes I want to check. Check that the values are the same, and then OBS and EXP plus equals 2. Well, that's bogus. Subscripted value is neither array nor pointer nor vector here. Oh, haha, I have a variable called exp within the macro. So a bit of thing that I'd forgotten about is that when you define macros, things you use within the macro kind of need to be specially handled so that they don't conflict with things outside the macro. There we go. Oh, better yet, instead of PTR, let's use indexes. So instead of that, we have ROM of expix. exp add is not const anymore. There we go. So those two, the first one worked. However, second one failed. Hold on, wait a minute. Oh. There should have been a warning there about the printf. Maybe there was, I just missed it. So at 81, oh, RAM at, OBS at. So how are we even getting to this? exp at 0, exp at 1, OBS at 0, OBS at 1. There we go. Oh 0800 11. Okay, so the second push is not happening. Oh, branch not taken, no push. So I put in a assumed push for every one of those branches. So really, we should be requiring 8 pushes, not 16, plus 1 is 9. So 9, this is going to be 18 here. Okay, down at the bottom. We should see call F pushed. Call NZ F1, so F3 should be, the F3s are not taken. So why is it that we got a 0 pushed there? I don't know. Let's do all the prints first. And the compares second. So 7F, 7E, 7D, 7C, 7B, 7A. We are decrementing stack pointer too many times. There we go. So from the top, a set of SP. In M1T5 of the call, we are decrementing it. In M4T2 of the call, we're decrementing it. And we're decrementing it again there, where we do not want to do that. So in the M5, we're not decrementing SP again, because it's a pre-decrement. Okay. Good thing I left those in. Okay, so the comparisons are looking pretty good here. 0, 8, 15, 23, 31, 3F, 4D, 5B, yada, 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 yada. And that worked. Okay. So, careful coding, yada. Yeah, right, careful coding. Anyway, sufficiently careful coding, combined with a lot of debugging, getting rid of the debug prints very carefully. So we still have this printing out the comparisons, and those still look good. So at the end of this loop, OBS at will have been decremented to point at, it will still be pointing at the last one that we observed, and the XP at will have been incremented past the last one we tested. So OBS at is the important one. So we will have tested the value at OBS at. So up to there, but not including there, it should be there. And then we say starting at 128 and running through RAM test area size should also be unmodified. There we go. And that is that. So call is now present and pushing. So quickly put to-dos in for the comments that I need to flesh out, and then I'm going to, I think, you know, if I implement return, I could be much more clever about this. So to call and return as a single test, I don't need to actually have this compare the RAM when I'm done. But the implementation of call doesn't change. We just need to implement return. So to do function comment. So if I implement return, let's leave call in place as it is so we can test the calls. It'll be the return instruction that will do a call return to verify it gets back to where it came. So if we ever have return to the wrong place, we want to fail. How are we going to do that? Also we've got return and we've got conditional return. So I'm going to need to push something on the stack and then do a return and see if it did it. This is going to be a bit more complicated assembly code because I don't want to just call and return and then dive into something else. I don't want to have a lot of different return points that all say success, or we could, go to the wrong place. Yeah. Yeah, the conditional return tests are going to be interesting. I think I can actually take the jump test. Instead of doing a jump or conditional jump, I can LXI the address, push it, and then do the return and verify things like, did I get to the right place on the stack and so on. Conditional return will not pop the stack if it doesn't take the path taken, which will leave me with some stuff in memory that I can test. Oh, there we go. Yeah, okay. So once we have this thing done, we will have things remaining on the stack from the branches not taken, jumps not taken. That works for me. Anyway, let's commit this. I am going to take a short break while I brush this up a little bit, push it to GitHub, and we come back. I'll swing into the next session where we'll do the return instructions. Yay! So until then, as I always say, keep it short, keep it small, keep it fast, and keep it safe.